Hello, everyone. My name is Jeff Procyse. I'll be leading the webinar today, and I assume that you can hear me. Also assume that you can see my screen, which is shared out. I'm going to wait just a couple of minutes to start, just in case people are running a little bit late after lunch or something like that. So if you want to go grab some coffee, use the restroom or something like that, take a couple of minutes to do it, then come back and we'll start having some fun. So I'll see you back here in just a couple of minutes. So let's go ahead and get started here and make maximum use of the time we have together. Again, my name is Jeff Procyse. I'll be your presenter today, and the subject of today's presentation is Principal Component Analysis, also known as PCA. And the subtitle is The Best Kept Secret in Machine Learning. Principal Component Analysis, to me, is one of those things that is absolutely essential to know about if you are a machine learning engineer or you're trying to become a machine learning engineer. It's something that almost everyone has heard of. A lot of people maybe have used it once or twice, but few people in my experience really understand it, and more importantly, understand just how important it can be to building operational machine learning models. So we're going to spend an hour or so together today. I'm going to introduce PCA to you. I'm going to describe how it works. I'll talk a little bit about the math behind it, but rather than get bogged down in the math, I'll work harder to build for you an intuitive understanding of what it does. I'll show you how to apply it using scikit-learn. I'll show you some great examples of how it's used and why you might want to use it. And then we'll take some time for questions at the end. Do feel free, if you have questions as we go along, type them into the question manager. I'll try to peek at that every now and then, but if I don't get a chance to do that during the presentation, I'll be sure to look at it once the presentation or the lecture part of the presentation is over. By the way, at the end, I'll give you some links to some resources, including a link to a GitHub repo where you'll find all of the code samples that I'll be showing today, as well as a lot of code samples that I won't be showing. So everything I'm showing here, you'll be able to grab for yourself and play with it, learn from it, build on it if you want to. So let's talk about principal component analysis. And first, why do we even care about PCA? If you work in the world of data science and machine learning, you may have heard of the term the curse of dimensionality. What the curse of dimensionality refers to is when we build a machine learning model, we prefer to train it with a data set that has as few columns as possible. A data set that has 10 columns of information versus a data set that has 10,000 columns of information is very different. And you may think, why would I ever build a model, train a machine learning model with a data set that contains tens of thousands of dimensions? Well, a common example of that is when we're training a machine learning model with images. If an image measures just 100 by 100 pixels square, then there are 10,000 pixels per image. That means the way machine learning looks at it as if this were a 10,000 column data set. So it's very, very common in machine learning to run across very high dimensional data sets. The curse is that the more dimensions we have, the harder it is to build a really good machine learning model. For one thing, more dimensions means the model's going to take a lot longer to train. 10,000 dimensions versus 10 dimensions, there will be orders of magnitude difference in the training time required. Another reason that we care about the number of dimensions is this. Sometimes when we're building a machine learning model and we're assembling the data to train it with, that data isn't easy to come by. In fact, machine learning engineers often spend a lot of their time just assembling the data sets to train with. So let's say you have a data set with 10,000 rows, that is 10,000 samples, and maybe it has 1,000 columns. Well, that's probably fine because there's a 10-to-1 ratio of rows to columns or samples to columns. But think about this, if it's an image data set that has 10,000 dimensions or columns and you have just 1,000 samples, you're probably not going to be able to train a very good machine learning model around it. As a rule of thumb, and it's just a rule of thumb, nothing more, you like to have at least 5 times as many rows in the data set as there are columns. Well, if you can't get more rows, if you can't get more samples, maybe you could reduce the number of columns and achieve the same effect. And in fact, that's one of the reasons that we use techniques like PCA to increase that ratio of samples to columns or samples to dimensions without having to go grab more samples. In fact, the little chart you see in the lower right of this slide shows something called Hughes phenomenon, which shows that for a given number of samples, as the number of dimensions in the data set that you train the model with increases, up to a point, the model gets more and more accurate. You're giving it access to more information. But once you pass that optimum number of features point, you're not adding any more samples, but you are adding dimensions. You can quickly get to the point that the model becomes less accurate because there's too much information in the columns. There are too few samples per dimension. So one way to solve that, again, see if you can reduce the number of dimensions, which is exactly what PCA does, then you can solve that problem. But there are a lot of other reasons that we care about dimensionality. The more columns of information there are, the more likely it is that there is multicollinearity between columns. In other words, 2 columns that are closely related to one another. If we knew that going in, we might just eliminate one of those columns, but it's often not easy to figure out which columns are multicollinear. And when we have a lot of multicollinear problems, it can make it difficult, if not impossible, to build an accurate machine learning model. Yet another reason we care about dimensions is because of visualization. Let's say someone asks you to build a machine learning model around a data set. Maybe it's a classification model. And the first thing you want to know is it even possible to build a decent model around this data set? Well, one way you could answer that question, if it's just a 2 or 3 dimensional data set, is to plot it using a library like matplotlib. Then, if you, for example, color code the different classes, you can visually see, is there enough separation between classes that I might be able to build a model? That's all fine and good for low dimensional data sets, but what if that data set has 100 dimensions or 1,000? You can't plot a 100-dimensional graph. You can't plot a 1,000-dimensional graph. But if you could somehow reduce the number of dimensions, compact them down to just 2 or 3, without sacrificing all of the information in the data set, then you could make a 2D or 3D plot of the data and have some idea up front whether you might be able to build a model around it. All of those are reasons that I call PCA the best kept secret in machine learning. What is PCA? The simple description is it reduces the number of dimensions in a data set. Well, on the surface, that doesn't sound very exciting. I could take a data set with 1,000 columns, lop 900 of them off, maybe using random selection. I'd have reduced the number of columns by 90%, but I've probably given up a lot of the information in the data set. In fact, I might have rendered it useless. The magic of PCA is that it lets you reduce the number of dimensions in a data set without suffering a commensurate loss of information. It's very common, for example, to reduce the number of dimensions in a data set by 90% and yet retain 90% or more of the information in the original data set. That's great because it decreases the training time for the model. It increases the ratio of rows to columns. It doesn't necessarily make the model more accurate, but in some cases it does. So PCA is first and foremost a technique for reducing the number of dimensions in a data set, probably a data set you're going to train a machine learning model with, but without giving up a commensurate amount of information. So how could you use this? Well, there are lots of applications for PCA in practice. One is you have a data set where the ratio of rows to columns is less than 5:1, and you'd like to increase that ratio thinking it might give you a better model, but for whatever reason, more samples are difficult to come by. If you could reduce the number of columns or dimensions without giving up a lot of information, then you could increase that rows to columns ratio. Another great use for PCA is for obfuscating data. I'm going to show you a really cool example of this shortly. Suppose you have a data set and you want to hand it off to another company that has expertise in machine learning for them to build a model around, but there's sensitive information in that data set. Maybe there's PII, maybe there's other information that cannot be divulged to the public or even to this partner you're going out to. With PCA, you can obfuscate the data. You can turn it into essentially a meaningless jumble of numbers without losing a single bit of the information in it, even though the person looking at the data and using it to train a machine learning model can't make sense of it, doesn't even know what the columns represent. If they can build a machine learning model around that data set, you can take that same model and train it with the unobfuscated data set that you keep in-house. Yet another use for PCA is filtering noise out of data, filtering out randomness. Almost all data has noise in it. There are several ways to do noise filtering and noise reduction in the data science world. PCA is one of the most effective ones, and I'll show you a great example of that in a moment as well. Another use case that we're going to look at is taking high dimensional data and reducing it to 2 or 3 dimensions so that we can do a 2D plot or a 3D plot and visualize the data, visualize the shape and the relationships, which could most likely impact the machine learning model that we build. It will tell us whether it's even possible to build one, might even influence the learning algorithm that we choose. And finally, one of the coolest use cases for PCA is something called anomaly detection. I'm going to show you a couple of examples of that. I'm going to show you, for example, how companies like Airbus send data from jet engines as they're flying around the world down to ground stations and run anomaly detection algorithms over the data to see if there are signs, for example, that the turbine wheel in that jet engine is about to fail. The beauty about anomaly detection is when you use techniques like PCA to do it, you don't have to have labeled data. You can literally look at raw data streams as they come in and say, huh, that looks anomalous. That looks okay. Ooh, that looks anomalous. There may be something that I need to look at here. So I'm going to show you how to do PCA-based anomaly detection. Now, before I start diving into the details, showing examples, looking at code, let me warn you about one thing. Before you apply principal component analysis to a data set to reduce the number of dimensions, it is rather important that the data be normalized. That is, that one column doesn't have a range of numbers from 0 to 1,000,000, while the column next to it has a range of numbers from 0 to 1. Now, data normalization and data standardization is a separate topic in machine learning, but it's not hard. And if in doubt, it never hurts to normalize before you apply PCA to a data set. Easy way to do that in scikit is to use classes like its standard scalar class, or you could on your own write a little bit of code that looks at all the values in a column, takes the average or the mean of the values, subtracts the mean from each value in the column, and divides each value by the one standard deviation in that column. That is a very, very common way to normalize data in machine learning. And one benefit of that is if there were previously columns that had widely different ranges, this will squeeze them all down to similar ranges, usually centered around 0, running between -1 and 1 and -2 and +2 or something like that. But you do not want to use PCA on a data set where you have columns with widely ranging numeric values in them. So let's talk intuitively about what PCA is and how it works. Remember that the big idea behind PCA is that we can take any arbitrary data set, we can reduce it to any number of dimensions we specify, and we can do so without giving up a lot of the actual information in the data set. A good way to visualize how this works is to see what PCA would do with a simple two-dimensional data set. So look at the diagram on the left here. I've manufactured a set of XY coordinate pairs. So it's a simple two-dimensional data set. They roughly fall along a line as you see there. It's a two-dimensional data set. So each point, each sample is defined by an X and a Y. Let's say that I wanted to reduce those two dimensions to 1. Well, if I simply discarded the column of X's, what I would be left with is a bunch of Y's. So I'd basically be projecting all those blue points over onto the Y axis. And the results probably wouldn't be very favorable because I've given up at least half the information in the data set. Same if I just decided to get rid of the Y column, all I'd have left is X's. If you can imagine all of those little blue data points projected vertically down to the x-axis, that's what I would be left with. And once more, I would be losing a significant amount of information in the data set. But here is effectively what PCA does. It uses mathematical transforms to define principal components or axes that define the data. And then when you ask it to reduce the number of dimensions, after having sorted these axes by how important they are, how much variance there is in the data along each axis, PCA by definition discards the axes that contain the least information. Now to visualize that, take a look at the chart on the right on this slide. It's the same two-dimensional data set, X's and Y's. On the left, you see those two black arrows. Those are the principal components or principal component axes. What PCA has done on the left there is determined that if it transforms the X and Y axis the way you see here, most of the variance is along that axis that runs from the lower left corner to the upper right corner. A little bit of the variance, some, but a lot less, is defined along that axis that runs towards the upper left corner. If I ask PCA to reduce this two-dimensional data set to 1 dimension, it finds those two principal component axes, and then it eliminates the one that contains the least information, the one with less variance. The effect of that is shown on the right. By getting rid of that short principal component axis, we're effectively projecting all those data points down onto the primary principal component axis. So we've reduced the number of dimensions by 50%. We've gone from 2 dimensions to 1, but you can see with those orange dots, we've retained most of the information in the data set. In fact, if you actually run this example, and I'll show it to you in a Jupyter notebook in a moment, you'll find that more than 95% of the original information is retained. We could recreate that data set as is with and only lose about 5% of the information inside it. Now, the way PCA works internally, not surprising, is a little bit math heavy. What we start by doing is building something from the data set called a covariance matrix. Covariance matrix is a square matrix. There's one column and one row for every dimension or every column in the data set. And the value in each cell of that matrix quantifies the variation between a specific pair of columns. Once we have the covariance matrix, we use a little bit of linear algebra to define the principal component axes. If you want to do a search on that and learn more, search on eigenvectors and eigenvalues, and you'll find lots of examples of how the math works. Once we've used those eigenvalues and eigenvectors to identify the principal component axes, then we do a little bit more linear algebra to transform the data points from their original coordinate system into that transformed coordinate system that we computed with the eigenvalues and eigenvectors. Now, the good news is you're never going to have to do that yourself. Why? Because libraries like scikit-learn do it for you and make it dead simple. Scikit gives you a class named PCA, all caps. If you want to take a data set of any arbitrary number of dimensions and reduce it to, say, 5 dimensions, it takes 2 lines of code to do it. You create a PCA object. With that in components parameter, you specify how many components or dimensions you want the data set reduced to. Then you call fit transform on the PCA object and pass in the data set that you want to have that transformed to. Now, how much information will be lost and how much is retained? I'll show you how to compute that in just a moment. But there could have been 1 million dimensions in this data set originally. Those first 2 lines of code in this slide reduce it to 5. There's another way to use the PCA function in scikit. If instead of specifying how many dimensions you want the data reduced to, you want to specify how much of the original information is retained, then you can do that by passing a floating point value to the PCA function. When you do that, scikit determines how many dimensions to reduce the data to in order to retain 80% of the original information in the data set. And in fact, after the fact, if you want to know how many dimensions remain, you can get that from the PCA objects in_components_attribute, as you see on the last line of code on this slide. Now, it really is that simple, and I'll show you some examples in a few moments. But before I do that, I want to show you something else kind of interesting. When you call fit transform to apply a PCA transform to a data set, you are reducing the number of dimensions in the data set, and you are giving up some amount of information. It may only be a small amount, but you are losing a little bit of information. You can use another PCA function in scikit called inverse transform to invert that transform. So you can say, reduce a data set from 1,000 dimensions to 100, then you can invert the transform and restore it to 1,000 dimensions. Now, why would you want to do that? Well, the first thing you need to realize is the data set that you get by inverting the transform will not be identical to the one that you originally applied the PCA transform to. Once you apply PCA and you reduce the number of dimensions, you have lost some information. So inverse transform restores the original number of dimensions, and the data set will probably look somewhat like it did before, but it will not be identical. Now, again, why would you want to do that? One of the reasons we do that is it forms the basis for PCA-based anomaly detection. So put a bookmark on that inverse transform method, and I'll show you a couple of examples momentarily that make good use of it. One question you're probably wondering is, when I reduce the number of dimensions in a data set by applying PCA, how do I know what the right number of dimensions is? How do I know how many dimensions to reduce it to? Well, there are a couple of ways to answer that question. It turns out that after you call fit transform on that PCA object, you can look at an attribute of the object named explained variance ratio, highlighted in blue on this slide. It's an array, it's a vector. It contains one value for every dimension in the reduced data set. And the value in each element of that array is a value between 0 and 1, telling you what percentage of the information in the original data set is explained by that dimension. If you actually plot these out, let's say you reduce a data set from 1,000 dimensions to 100. The explained variance ratio attribute will be an array with 100 floating point values. The 0th element in the array will be the highest value. The next element in the array will be the next highest value, etc. Remember, PCA is by definition sorting these principal component axes from top to bottom, from those that contain the most information from the data set and those that contain the least. And if you sum up those values, that tells you how much of the original information in the data set that you PCA'd was retained. In fact, you can plot those explained variance ratio values. The chart you see here on the left, I'm just plotting all of the values in that array. And what you see there is, in this case, it looks like about 18% of the information in the original data set was captured in that very first dimension. The further to the right you go, further into that array representing lesser principal components, the less information is contained. So you can see in this example, and from this example that I drew this chart from contained about 3,000 dimensions originally. I reduced it to 150 dimensions. In other words, I lopped off almost 95% of the dimensions. And you can see that by the time we get out to the 20th principal component or so, doesn't matter if we lop those things off because they contain so little information. In fact, looking at this plot on the left, which we call a scree plot, I reduced it to 150 dimensions. I probably could have reduced it to 40 or 50 with almost no significant difference. Another way to look at the same data is to plot a running total or running sum of the values in that explained variance ratio array. That's what you see in the chart on the right. And what we can discern from that is, let's just go out here to the number of components, 60 principal components. We can see there, if we go up, that with the first 60 principal components, we're capturing almost 90% of the data in the original data set. So doesn't matter how you look at it, but if you're trying to determine, okay, I'm going to reduce the number of dimensions in the data set, but what number should I reduce it to? This is one way to make that determination. Looking at how much of the information in the original data set is captured in the individual principal components, so you can decide how many to lop off. Let's look at an example or two here. And to do that, I'm going to pop over into a Jupyter notebook. This is one of several notebooks in a repo that I'll give you a link to at the end here. And I just want to show you here a couple of things about how principal component analysis works. So you already know, for example, that if you take a simple two-dimensional data set like this one and reduce it to one dimension, in this example, PCA will find the two axes or principal component axes that the data lies along. And when it eliminates one of those dimensions or one of those components, it will eliminate the one that contains the least information, effectively projecting all of those blue points here you see down onto the principal component axis here, and you can see those projections in orange. But let's look at some examples here. So here in this Jupyter notebook with a little bit of Python code, I'm loading a famous data set called the labeled faces in the wild data set. In fact, it's built into scikit-learn. It goes out and downloads it externally, but it's used so often in examples and in teaching scenarios, Scikit just makes it available with a single line of code. I've loaded the data set in such a way, there's something like 13,000 facial images in the whole data set. I've told Scikit only to load images of people for which there are at least 100 faces per person. And it turns out there are 5 of those in the data set: Colin Powell, Donald Rumsfeld, and a handful of other famous people. So I've loaded the data set here. Here's what the first 24 images in the data set looks like. Each image measures 62 by 47 pixels. That means each image has 2,914 columns or dimensions. So it looks pretty simple, but this is an almost 3,000 dimensional data set because there are that many pixels in each image. So what I'm going to do is use PCA to reduce the number of components from almost 3,000 to 150. In other words, I'm literally getting rid of about 95% of the columns in this data set. So I create a PCA object. I specify that I want it reduced to 150 components. I pass all of those facial images into the fit transform method, and then I plot the results. So here's what's interesting. If you compare images up here to images down here, let's look at that first image of George Bush right here under the cursor. That image contains almost 3,000 dimensions, almost 3,000 pixels. Here's the same image reduced to 150 dimensions. We reduced the number of dimensions by almost 95%, but the image looks almost the same. It's a little bit blurrier, but here we can see very graphically that even though we reduced the amount of information in the data set or number of dimensions by almost 95%, we didn't give up that much information. In fact, let's see here. Actually, what I've done right here is I have shown the un-PCA'd faces. So let me be a little bit clearer. I PCA'd these facial images up here with the call to fit transform. Then I inverted the transform so that we could see what the facial images now look like and visually see how little of the information was lost. So one question to ask is, okay, we reduced the number of dimensions by about 95%. How much information did we lose? Well, look at this. I'm simply summing up all the values in the PCA object's explained variance ratio attribute, and I retained almost 95% of the information in the original data set. So how about that? I reduced the number of columns by almost 95% from almost 3,000 to 150, but I lost only about 5% of the information in the original data set. And here, by using facial images, you can see very graphically that not a lot of information was lost. Here's a little bit of code that does the scree plot showing how much of the information in the original data is encoded in each of these, lost my cursor there, in each of these dimensions. And here's a plot of the running total. So I can say, for example, with if I said just 100 dimensions, and I go up here, I could see from this chart that I'm capturing about 90% of the data had I reduced it from 150 dimensions to 100. Now, let's make this a little bit more practical. One of the reasons that data scientists like PCA is because they can use it to filter noise from data. And I'm going to give you a very graphic example of that as well. Take a look at this. Here's another famous data set, University of California Irvine data set of scanned handwritten digits. Each digit is an 8x8 scan. If you squint your eyes a little bit, you can kind of see what these digits represent: zeros, ones, twos, threes, and so on. You can also see they were handwritten because each one looks a little bit different. So it's not too hard to build a machine learning model around a data set like that. But what if that data set were noisier? What I've done here is I have used NumPy to introduce random noise into the data set. And I think you'll agree that this isn't nearly as clear as the original. In fact, sometimes it's difficult to tell, looking at one of these images, what digit it represents. But remember, one way to do noise filtering in machine learning is to apply PCA to the data and then invert the PCA transform. Remember, when you reduce the number of dimensions with PCA, it is by definition discarding the dimensions that contain the least information. Well, noise tends to have the least informational value. So if you lop off a few dimensions, then restore the original number of dimensions, chances are the data you're getting rid of was the noise, because it tends to be the less important. Let's try it. So we take this very much noisified image data set. I here apply a PCA transform to reduce it to 50% of its original information, not dimensions, but information. It actually reduces the data set, in this case, from 64 dimensions to 12. Then I invert the transform and plot the results. And while these scans are not as clean as the original ones, they're a lot cleaner than the ones I added the noise to. And now it's not too difficult by eye to look at these and tell what digit each scan represents. So another use for PCA is to remove random noise from data this way. And again, it's not the only way to do it in machine learning, but it's one of the most common ways to do it, and also sometimes one of the most effective. Another reason that PCA can be so useful is visualizing high-dimensional data. Assuming you're a human being like I am, I can't plot data in more than 2 or 3 dimensions. I can't make a 10-dimensional chart, and I can't even envision in my mind what it should look like. But what if, again, you were given a data set, you want to determine if you can build a machine learning model around it, and the first thing you want to do is somehow visualize the data to see if there are boundaries of separation that might be useful to a classifier, for example. So let me show you how you do that in code, and then show you a couple of examples of that being used in real life. So in this case here, I take a data set. Regardless of how many dimensions it has originally, I reduce the number of dimensions to 2 using PCA. Then I apply that PCA transform and I plot the resulting data. I can't plot a data set with 100 dimensions, but I can reduce it to 2 dimensions with PCA and plot that 2-dimensional data set. The key here is, most likely, I've still retained most of the information in the original data set, so hopefully the plot will still be meaningful. Just as an aside, I wanted to make you aware that there are other dimensionality reduction techniques in machine learning that are sometimes used with or in lieu of PCA to reduce high-dimensional data sets to 2 or 3 dimensions, specifically for the purposes of visualization. One of those is called T-SNE, which stands for T-distributed stochastic neighbor embedding. It is a dimensionality reduction technique. Mathematically, it works very different than PCA, but the results are the same. You can reduce any data set to 2 or 3 dimensions so you can plot it. And whereas with PCA uses linear algebra to do the reduction, T-SNE uses a nonlinear reduction technique. And sometimes it's useful if you're going to reduce high-dimensional data to 2 or 3 dimensions to plot it, to try it with both PCA and T-SNE. The results will usually be substantially different, and a lot of times one of the results will be more meaningful than the other. So let me just show you an example of dimensionality reduction used for the purpose of visualizing high-dimensional data. So back to that same notebook. What I'm doing here is loading that same digits data set, this 64-dimensional data set that you saw right up here. Now, there are 10 different classes represented in this data set, one for each of the digits 0 through 9. And let's say I want to build a machine learning model around it. First thing I might want to know is there enough separation between the classes that it's even conceivable to build a machine learning model? Well, I can't plot a 64-dimensional data set in order to visualize it. But you know what I can do? I can use PCA to reduce those 64 dimensions to 2. Then I can use matplotlib to plot the result. And this is what I get if I do it. And I can look at this. Each color in this chart represents a different digit, 0 through 9. You can see that legend on the left. And the first thing I notice here is there does seem to be a reasonable degree of separation between the classes. For example, light blue represents scanned handwritten zeros. Dark blue represents scanned handwritten ones. And the fact that there's very little overlap between the light blues and the dark blues tells me, guess what? A machine learning model can probably distinguish between them pretty well. Now, it's not quite as good with other digits. For example, there's a fair amount of overlap between the reds, which represent 4s, and the light purples, which represent 6s. But remember, we can't totally trust that because we have literally reduced 64 dimensions to 2. It's easy enough to do 3D plots in Python using libraries like matplotlib3D. Here, I'm using PCA to reduce the 64 dimensions not to 2, but to 3. Then I'm using matplotlib3D to do a 3D plot. Now, if this notebook is running live, this is an interactive image. You can drag with the mouse to look at it from different angles. But even in the static image version of it, look at this. In 3 dimensions at the right angle, you can see that there's quite a bit of difference between the light purples here and the reds. So what appeared in 2 dimensions to be some concerning overlap in 3 dimensions doesn't look so bad. Now, what if I plotted that same data set in 2 dimensions with T-SNE rather than PCA? T-SNE takes longer, it's more compute intensive, but scrolling back up, here is a plot of the PCA version of that 64-dimensional data set. Here is a plot of the T-SNE version. And what T-SNE tends to do is exaggerate the difference between the classes, which can be very appropriate when you're seeking to build a classification model. Here, with those differences being exaggerated a bit more, you can see that it looks like it would be entirely reasonable to build a machine learning classifier around this data because there's not a lot of overlap in that T-SNE derived chart. So I hope that's interesting so far, but guess what? We haven't gotten to the really fun stuff yet. So let's move on. Remember that another use for PCA is to obfuscate data. Again, a use case is you're contracting out the building of a machine learning model. You have some very sensitive, very proprietary data. You have to give it to the firm you're contracting to train the model, but you really don't want them to see what's inside it. So one thing you can do is you can obfuscate the data set with PCA. So the trick is you reduce the data set from M dimensions to M. You're not really removing any dimensions or any columns, but the effect of reducing, say, a 100-dimensional data set to 100 dimensions is that all the numbers get jumbled so that they're totally meaningless. In this example on the slide, it's a very simple example. I took that 3-row, 3-column data set you see in the lower left corner. I applied PCA to it, as you see in the code above, and in the lower middle of the slide, that's what the numbers were changed into. There's no discernible relevance to their original meanings, nor can anyone look at it and make sense of the values in the columns unless they can invert the transform, which they can't do without the original transform. It's almost like applying a one-way hash. As long as that hash algorithm is mathematically sound, you can't work backward from the hash to the original data. Now, this is actually used quite a bit in the real world. The beauty of this is because you're not actually removing any dimensions from the data, you're not removing any information either. In fact, if after reducing a 100-dimensional data set to 100 dimensions, if you sum up the values in the explained variance ratio attribute, the sum will be 1.0, telling you no information was lost. If you can build a machine learning model around this, the PCA version, then you can build a machine learning model around this. But over here, no one outside of you who applied the PCA transform knows what these numbers mean or how they were arrived at. I'm going to show you an example of that in the real world in just a moment. But before I do that, let's talk about PCA as a technique for doing anomaly detection. Now, anomaly detection is a branch of machine learning. Normally, when we think about machine learning, we think about supervised learning for making predictions, unsupervised learning, for example, doing cluster analyses to extract insights from data. But there are other types of models we can build in machine learning. There are recommender systems, for example, to recommend movies or products that you're selling online to increase your sales. In fact, Amazon claims that about 30% of their sales are driven by the machine learning recommender systems that they use. That's why, you know, when you drop an item into your cart at Amazon, you go to check out, you often see something like, hey, you might also be interested in these products. They are using machine learning to decide what products to present to you, and they're increasing revenues as a result. But yet another branch of machine learning, a different type of model you can build is an anomaly detection model. And the purpose of an anomaly detection model is to detect anomalous samples. If it's vibrational data coming from a jet engine, and you've collected samples when that engine is running fine, then you simply take all the new data coming from that jet engine, run it through an anomaly detection algorithm, and it can tell you, well, maybe it's not so fine after all by comparing it to what you've defined as a normal range. There are lots of ways to build anomaly detection models in machine learning, one of the most effective and arguably the most common way to do it is to use PCA. How does it work? Well, remember this. Remember that with PCA, you can take a data set with an arbitrary number of dimensions and you can reduce it to some lesser number of dimensions. You can also then invert the transform to restore the original number of dimensions, but because some data was lost when you originally reduced the number of dimensions, the restored data set won't be perfectly identical to the original data set. The theory behind PCA-based anomaly detection is this. If you PCA and then un-PCA a sample that is not anomalous, the reconstruction loss, the difference between the original data and the reconstructed data will be small. But if you apply that same transform and inversion to an anomalous sample, the reconstruction error will be greater. And you can use that difference to determine which samples are anomalous and which ones are not. So let me just jump right into a couple of examples here, which I think you'll find somewhat interesting. I'm going to pop off over into my Jupyter notebooks again to do this, but I'm going to run some different Jupyter notebooks. So first off, let me show you this. Here is one example of how to do credit card fraud detection in machine learning. It was fraud detection that originally got me interested in machine learning about 10 years ago. I got a couple of calls from American Express about a year apart. Someone had stolen my card number, tried to use the card to buy crazy stuff. Once it was an airline ticket in Brazil. American Express caught the fraud both times, called me, said, "Was this you?" And I said, "No." They declined the charge, they canceled my card, sent me a new one. About 10 years ago, though, something happened that really opened my eyes. Someone used my credit card number to try to buy an expensive necklace. Well, expensive, it was about $700 in a jewelry store, but it was just 2 miles from my house. My phone rang. I was working in my office in the basement that day. It was American Express. They said, "Did you just attempt to buy a necklace at such and such a jewelry store down the road?" And I said, "No." They said, "No problem, we'll decline the charge." I said, "Wait a minute. That could have been me. That store is 2 miles from my house. And yes, I do occasionally buy nice things for my wife. So how did you know it wasn't me?" And the lady on the phone said, "We just know, sir." Well, it turns out that credit card companies were some of the earliest and most successful practitioners of sophisticated machine learning models. Every time you use your credit card, the data defining that transaction goes through one or sometimes several very sophisticated machine learning models trained sometimes on billions of transactions. And it can determine with a very high degree of accuracy whether a transaction is fraudulent or not. So I thought maybe I could build a model like that myself. So yeah, it's not too hard to do. Now here, this is not using anomaly detection. This is just straight up machine learning, building a binary classifier to see if we can detect fraudulent credit card purchases. So I start by loading the CSV file. There are, I think, 284,000 rows in this data set, each representing a credit card transaction. Here's what the first 5 rows of the data set looks like. You'll notice that while some of these columns have a clear meaning, this is the amount of the transaction. Class is either 0 for a legitimate transaction or 1 for an illegitimate transaction. Everything else is just meaningless. The columns have meaningless names like V1 and V2. The values in the columns have no idea what they mean. Can you guess what's happened here? This data was published a few years ago. It's real credit card data from 2 months of activity of European cardholders. But they could not publish the raw data. There's PII in there. There's proprietary information that that the credit card companies was not willing to give up. So can you guess what they did? They applied PCA to it to obfuscate it. They applied it to these columns named V1 through V28. Now they can publish this data set so people like you and I can try to build machine learning models around it, but we have no idea what the actual data that they're capturing is. So there is PCA being used to obfuscate data so that you can give it to others for their consumption. And again, because no information was lost here, if I can build a machine learning model around this, the same model should work equally well with the original un-PCA'd, unobfuscated data set. So what I'm doing here is just looking at some basic stats. I see that there are no missing values in any of the rows, which is good. Here I'm checking for class imbalance, and I find out, not surprisingly, that this is a very imbalanced data set. There are 284,000 something rows in the data set that represent legitimate transactions, only 492 that represent fraudulent transactions. That's not surprising because there are a lot more legitimate credit card purchases than there are illegitimate ones. But it does mean that knowing that we're going to be training with a highly imbalanced data set, we need to be very careful about how we analyze the results when we test the model. And I'll say more about that in a moment. So what I do now is simply do the normal train test split on it, doing an 80-20 split on the data. So I'll train the model with 80%, use 20% to test it. This stratify equals y parameter tells scikit, when you do the split, make sure that the proportion of zeros and ones, or legitimate and fraudulent transactions in the test data set and the training data set, are the same as those proportions in the original data set. If I don't do that, there's no telling what this model is going to do. It could appear to be super accurate. It could appear to be not accurate at all. I then build a simple logistic regression model and train it here with the call to fit. And look at this. With logistic regression, one of the meat and potato classification algorithms in machine learning, it can look at the transactions in the test data set, and it does a pretty good job of picking out the fraudulent transactions. Here, in the legitimate transactions it examined, it got it right in predicting they were legitimate 56,853 times. It missed it 11 times. That's probably acceptable. You never want to bother a customer by turning down a legitimate transaction. By the way, 15 minutes before this webinar started, I got a text message, then a call from my local bank reporting potential fraud on my Visa card. So it was actually turned out to be a legitimate charge done by my wife, I think. So their machine learning model didn't work well. It was one of these 11 that said this may be a fraudulent transaction when it really wasn't. So look at this. Because there are many fewer samples of fraudulent transactions in this data set, the model isn't so good at spotting fraudulent transactions. It gets it right about 2/3 of the time, but that's okay because this is what credit card companies want. They never want to bother a customer by declining a legitimate transaction. They want to minimize this number right here, or frankly, minimize this percentage, this number divided by this one. Here, if they can catch 2/3 of the fraudulent transactions, that's fine. That's not 90%, it's not 98%, but what's important to them is they are rarely misclassifying a legitimate transaction as a legitimate. Now that was with logistic regression. Could we do better with other learning algorithms? Here's the same model, this time using a random forest classifier and same data set. And guess what? It only misclassified 4 legitimate transactions, and it did a slightly better job in picking out the fraudulent ones. Just for grins, I tried using a gradient boosting machine, a gradient boosting classifier, and found out it wasn't quite as good as the random forest. So here, using a traditional supervised learning machine learning model and a random forest classifier, I can do a pretty good job of picking out fraudulent transactions. I can catch over 2/3 of them while rarely ever misclassifying a legitimate transaction as fraudulent. But again, this is not PCA. This is not anomaly detection per se. This is traditional supervised learning. Here is the anomaly detection way to go about doing the same thing. Fraud detection with unsupervised learning. Here's what I do. I start with the same data set. And again, the data set was PCA'd by the organization that published it to protect the sensitive information inside it. Then I basically separate the samples by class. I create one data frame that contains all the legitimate samples and another data frame that contains all the samples of illegitimate transactions. And then I PCA them. I PCA them separately. I apply PCA, I reduce the number of dimensions, which I think is 29 to 26. And I do that separately for the legitimate transactions and for the fraudulent transactions. Then I invert the transforms. Then I define a little function, a helper function, and get anomaly stores. What it does is it takes two data frames, one that represents the data before PCA is applied, one that represents the data frame or data set after PCA is applied and inverted, and it measures quantitatively the difference between the two. So I measure those scores for both the legitimate transactions and the fraudulent transactions. I'm measuring the reconstruction error. Is it possible that the reconstruction error in applying PCA to a fraudulent sample and then inverting the transform will be higher than the average reconstruction error when I do the same to a legitimate transaction sample? Well, the short answer is yes. Here I plot it, and from this I had to do a little bit of playing around, but bottom line is this. What I did is I chose a threshold of 200 on this chart you see right here. This is the amount of reconstruction error that was occurred in PCAing one sample, inverting the transform, and then measuring the reconstruction loss. And what I find is this: if I choose the threshold reconstruction loss of 200, I can take any one sample representing, for example, a transaction that just occurred. I can compute the reconstruction error that I get when I PCA it and un-PCA it, and I can use that to determine if the transaction is fraudulent. Now, it's not quite as good as supervised learning. It rarely is. It got it wrong 76 times out of 284. Actually, that's not much worse than the original, since I ran many more test samples. It got it right wrong 76 times when looking at legitimate transactions. It wasn't quite as good as supervised learning in picking out the fraudulent ones. It's about 50-50. So it lets about half the fraud slip through, whereas supervised learning let about 1/3 of the fraud slip through. But this is PCA used to do anomaly detection. And remember, the beauty of anomaly detection is it doesn't require labeled data. Now, I used the labels in this case to derive my thresholds, but it wasn't absolutely required. In fact, in the next example I'll show you, we do not have labels. We're dealing with completely unlabeled data and using PCA-based anomaly detection to tell when something's about to go wrong. Let me show you this final sample here, then we'll close out. This final sample I call fraud detection. What did I name? Anomaly detection PCA. So one of the classic uses for anomaly detection in machine learning is predicting failure in machinery, especially rotating machinery like gears and turbines. This is used a lot by the aircraft industry to predict failures before they occur in jet engines. You would obviously rather have that ring in a big GE turbofan engine replaced a few hours before it fails than when it actually does fail. And PCA-based anomaly detection is one way data scientists often do that. So here's what I did. I downloaded a data set. It's in this file, bearings.csv. It's real data published a few years ago by NASA. What they did is they took a steel shaft, mounted it on 4 bearings. They spun the shaft at, I believe, 2,000 RPMs. They had very sensitive vibration sensors on each of the bearings, and they ran the thing until one of the bearings failed. They captured all the vibrational data from the bearings and they published it so machine learning engineers like us could use it and learn from it. So here's what it looks like. There are 4 columns, well, 5 columns. One is a time column. The other 4 columns are the vibrations from the 4 bearings. When I plot the vibrations, you can see what they look like. And here it looks like bearing number 1, a few days into the test, got sort of jittery here, then vibration started going way up, and boom, here it failed catastrophically and actually took some of the other bearings with it. So wouldn't it have been nice if we'd been able to predict maybe way back in here that a problem was about to occur so we could replace that bearing before it actually failed? So here's how I do that with PCA-based anomaly detection. And I'll just quickly walk through this. Remember, I'll give you a URL so that you can download these code samples and look at them more if you want. What I'm doing is first using PCA to reduce the 4 columns in the data set representing the vibrations of the individual bearings. I'm reducing it down to 1 component. And I'm plotting it here. Not surprisingly, when one of the bearings begins acting up, it affects the PCA data, because remember, when we discard that dimensions with PCA, we are by definition getting rid of the least interesting or least meaningful data. Just for grins here, I then inverted the transform to see if I could recreate the original data, going from 4 dimensions down to 1 and back to 4. And it's actually pretty good. You can see that the shape of that chart at the top is not that different from this one. But the real reason I combined it all into one was I wanted to pick a threshold here that might tell me that if any one bearing goes above that threshold, it might be a sign of impending trouble. So what I've done here is I've plotted the reconstruction error when I apply that PCA transform to data, one data point, one point in time for the 4 bearings, and then invert the transform, and I can see that indeed somewhere here, when I get this little blip, that was the first indication in terms of the reconstruction error of the sample that something might be going wrong. So then I just wrote a little function named isAnomaly, which takes the threshold value, it takes the original bearing data, and the PCA transform that I'm going to use to reduce the dimensions and then invert back to the original number of dimensions. And what I find here is to visualize this, I'm shading in red the times when there are indications that something bad is about to happen. And by choosing different thresholds, we can adjust the sensitivity. Here, it would have told me earlier that one of these bearings was about to fail, but you can also see that the red stripes aren't real consistent here. We are getting some early indications that failure may occur, but some of those we may interpret as false alarms. Here, with a higher threshold, we learn about 3 days out that one of the bearings is going to fail, but there's a hard edge here. We're not getting a lot of ons and offs, making us wonder if it's a false alarm. So again, wish I had about 30 minutes just to go through all the nuances and the subtleties, but it's a great example of PCA-based anomaly detection applied to a real-world problem, predicting failure in rotating machinery. Now, before I take questions, let me just go back to a couple of slides to close this out. Just a quick summary of what we've talked about. PCA is a very important technique for reducing the dimensionality of data. And we've talked about all the different reasons that you might want to reduce the number of dimensions. For example, to increase the ratio of rows to columns, to do noise reduction, noise filtering, to reduce the number of dimensions down to 2 or 3 so that you can plot the data and get some visual, human sense of what the data looks like. You can use it to obfuscate data without losing any of the information in it. And you can basically implement an entire branch of machine learning that is build anomaly detection models by applying PCA to do that. And Scikit's PCA class makes that extremely easy to do. It hides all the math, reduces all of this stuff to 1 or 2 lines of code. It's just great. So final thing before questions, if you would like these Jupyter notebooks that I showed you, I store those and a lot of others in a public repo on GitHub. You can see the URL here. Feel free to go there, download all the cool samples in that repo, and check back from time to time because I'm constantly adding new samples and revising existing ones. Also, this session, this webinar, came from a much longer course that I wrote and teach for companies and research institutions around the world So it's a lot of fun. It's all about ML and AI. It's not heavy on math. It's all about building intuitive understandings. If you'd like to know more about that course, there's a bit.ly link here for you to do it. Also, we have a free, an on-demand developer training service called Winelect Now. It's at winelectnow.com. This session is already on there, as well as a bunch of other machine learning sessions that I and others have recorded. Normally, you have to plop down a credit card to use it, but since you attended the webinar, if you want 14 days free, just use that final link there. It'll ask you to create an account, email address, password, a couple other things. You don't have to provide a credit card or anything like that. It's 14 days free on us. You can go wild and party on everything machine learning or .NET 5 or React or Angular or whatever else you want to do, because we have a lot of great content there. So let me pop over to the question manager and see if there's some questions I can answer for you. Doesn't look like there are a lot. Why don't we open up the mics? Rachel, can we open up the floor so anybody can ask questions verbally? Do you know?
That part I'm not quite sure how to do.
Well, I tell you what, Rachel.
We can start with the questions.
Okay, now I only see one. Do you see more?
Yeah.
Oh, wait a minute. There are more, but I can't read them because this window is so small. Yeah. Do you want to pick 2 or 3,
Yeah,
Rachel?
sure.
Okay.
Let's see. Do you find the AI tools from Microsoft and Azure, or around Watson, IBM tools around Watson to be more useful?
It's a great question. So I don't have a lot of hands-on experience with the Watson tools. I do a lot with Azure Machine Learning, Azure Cognitive Services. So I can't really make an educated comparison of the two. I know that there's a lot of overlap. They do a lot of the same things. They do it in different ways, but I do use Azure Machine Learning and Azure Cognitive Services a lot and find it incredibly useful. As for doing a meaningful comparison, I can't do that. But Rachel, you could probably do that, right?
Right.
Right.
Yeah.
Rachel is going to hit me after this is over.
Exactly. Okay. The next question: if the credit card company ran PCA on their data set, how can you use that data afterward? You cannot test any data since you do not know what the column means.
You're exactly right, and that's very perceptive. So when we take that PCA data set from the credit card company, we can train a machine learning model from it. We can test that model with samples from the same data set that we've broken off and not used for training. But in terms of using it for doing future predictions, we can't take the data regarding or defining a transaction and transform it the same way to do it. So you're exactly right. So unless the credit card company will give us an un-PCA'd version of the data, we can build the model, we can train it, we can test it. We can't actually make predictions against future data from it. However, we could give the model to the credit card company, and because they know how to PCA a transaction to feed it into the model, they could do predictions with it. We can't. They can, because they know how the original PCA transform was defined. So I hope that answers your question. It's a great question, very perceptive of you to pick up on that.
Next, are PCA used for development of driverless cars?
It's a great question. Is PCA used for the development of driverless cars? To my knowledge, the answer is no. I am pretty familiar with the algorithms and learning methods used for driverless cars. If that's something you're interested in, I recently did a pretty good blog post on it. The title of the blog post is Object Detection, and it describes how driverless cars use very specialized CNNs, convolutional neural networks, to detect objects and images, and then to identify objects in those images. To my knowledge, none of the self-driving cars today use PCA as part of that process, but unless Tesla and others are willing to share their source code with me, I couldn't tell you for sure, but I suspect there's no PCA there. For self-driving cars, it's very much an object detection and image classification problem. It's all done with convolutional neural networks, and that's where a lot of the research money is poured into in that branch of machine learning. What else you got, Rachel?
Okay, and hopefully I can say this word. Can the obfuscating feature of PCA also be used for augmenting data? For example, if I obfuscate my limited data of size 100 and then join it with the original data, do I now have data of size 200?
Boy, that's a great question. The short answer is I can't tell you definitively yes or no, but it's a very interesting idea, and I would encourage you to try it and tell me if it works. And where that question comes from, you know, when we train a machine learning model, generally speaking, we want as much data as possible. Now, yes, there can be too much data, it can take the model too longer to train. But, you know, typical model, if we're going to get a better model if we have 10,000 samples to train with than 100 samples. But it's not always easy to generate those additional samples. So data augmentation is taking the data that you have, transforming it slightly so that you can basically increase the number of samples artificially. It's used a lot in image classification problems in deep learning, specifically with convolutional neural networks. I'd never thought of this, to be honest, but it's conceivable that I could use PCA to artificially increase the number of samples while remaining consistent with the original shape of the data, thereby doing data augmentation and maybe produce a better model. Honestly, don't know, but it's a fascinating idea, and I wouldn't rule it out until I gave it a try. It's a great idea. Rachel, we need to hire that person to get their contact.
Yeah, right.
Yeah.
Okay.
How about one more? And then what we'll do, Rachel, we'll do one more, and then I'll make sure my email address is back up here. If people have additional questions, they can email. What's the next thing you want to do?
Okay. Do these principles apply to network data? I'm trying to find anomalies in Wi-Fi and wired networks.
Absolutely, that would be a great application for PCA-based anomaly detection. In fact, I don't know of the specific details, but I am aware of at least a couple of specific instances in which PCA-based anomaly detection has been used to do that. Look for anomalies in Wi-Fi data, to look for anomalies in patterns of traffic to websites, for example. I actually spoke to an engineer who was in one of my classes about 6 months ago, who was doing something really interesting on the hardware side with the bus in a computer, and was thinking about using anomaly detection to look for anomalies in the signals on that bus that had something to do with invalid cache hits or something. He was, you know, much more of a hardware engineer than me. But generally speaking, yes, this anomaly detection, remember the theory behind PCA-based anomaly detection is you just take a bunch of arbitrary samples representing signals or patterns that you would classify as non-anomalous, then take some that you would classify as anomalous, apply PCA to both data sets, then invert the transforms, look at the reconstruction loss, and if you can see a substantial difference in the reconstruction loss there, then you can apply PCA-based anomaly detection to that problem. Okay, Rachel, just for fun, one more, and then we'll respect everyone's time and call it a day.
Okay, here's one. What was the reason you chose to use 26 dimensions for your dimension and ML example?
That's a great question, and I didn't address that. So the original data set had, I believe, 29 dimensions, and in that that example of credit card fraud detection, I used PCA to reduce it to 26. Very perceptive of you. How did I choose that? I chose it through trial and error. Here's what I found. I tried different values like 28, 27, 26, 25, 24, and I did the math, applying the PCA transforms to the data, inverting it, measuring the reconstruction error, and I found that the magnitude of the reconstruction error was the highest when I reduced the number of dimensions from 29 to 26. So it was purely trial and error. Of course, machine learning engineers never say trial and error. We say it was empirical, right? But it was trial and error. A really good point to follow up on there is, when you do PCA-based anomaly detection, there are usually two things that drive the accuracy of the result. One is the number of dimensions that you choose to remove from the original data set to do the deconstruction and deconstruction. The other is the threshold that you pick for defining what is an anomalous sample and one is not. And what we typically do is we empirically, that is using trial and error, we experiment with different numbers of dimensions and different thresholds until we find the model that best does what we want it to do. So I can honestly say, Rachel, that this may be the smartest set of questions I've ever gotten from one of these webinars. So I'm excited.
Awesome.
Thank you. Thank you, all of you, for sitting in. And I think you can see the cover slide here with my email address there. Some of you may be wondering, wait a minute, I thought Jeff worked at that company called Winelect for 20 years. Well, last year, Winelect and Atmosera merged. We do some things they don't. They do some things that we don't. And now we're one big happy family and are just having a blast. One of the things we love dealing with is data, machine learning, and AI. So if I can ever answer questions for you, help you with a problem you're having, or you're even interested maybe bringing us in to do a class, feel free to reach out to me at jeff.proseiss@atmosera.com, and I'll be glad to help you if I can. So, well, thank you. I hope that this was time. Yeah, hope it was time well spent. Hope you're a little bit smarter now than you were an hour and a half ago. Hope to get to meet some of you in person someday. Thank you so much. And Rachel, thank you for putting everything together for us.
Thanks. Okay, see you guys next time.